So integration by substitution I alluded to in the previous examples. It's the closest we get to a chain rule, really, in terms of anti-differentiation. And what we sort of do is we substitute out a complicated expression, okay, much like the chain rule, and we do some differentiation and change the variables around. Now the process only works if the function that you substitute for, its derivative has to be present in the function, okay? I guess when we look at linear functions, it's a little bit of flexibility on that, but for anything but a linear function, if the derivative isn't present, so in this example here, I'm substituting in for x squared plus 3, the derivative of that is 2x. And whilst it's not 2x, it is x, so we can introduce a constant to make it present, okay? So that's the fundamental, most important process or part of the process. So if we actually look at an example here, I'll talk to you about it. So we can look in here, we can see, normally you might look at a polynomial function or a polynomial function and try to expand it. But obviously something raised to the power of a half is very difficult to do that. So what we do is we look at that complicated expression and we substitute it out, okay? So if I put u equal to x cubed minus 1, that means the derivative of that function is equal to 3x squared, okay? Now, what we want to do now is, I've got this function over here, and we try to express this function now in terms of u. And we should be able to make it a simpler function in terms of u. So I've got to be able to replace 5x squared, x cubed minus 1, and dx to be all expressions in terms of u. So the key to that is this du dx part here. If du dx is equal to 3x squared, I guess if I multiply dx across, it means that du is equal to 3x squared dx. And I'm going to bring the third back. 1/3 du is equal to x squared dx. So now, all right, let's have a look at this function here that's all in terms of x. That 5, undo that. That 5 can be a constant out the front, just a constant. X squared dx. X squared dx is there, and that's equal to 1/3 du. 1/3 du. That leaves me with x cubed minus 1 to the power of a half. X cubed minus 1 is u, so that's the same as u to the power of a half. So if I tidy this function up then, an equivalent integral is 5/3 integral u to the half du. Okay, how much easier is that to integrate? All right, and so that's the beauty of our u substitution. If you have the derivative of the thing that you substitute in for present, well then it makes it a very nice process to implement. All right, so now if I anti-differentiate, I get 5/3, add 1 to the power, u to the 3/2 over 3/2. So that's 5/3 times, flip it upside down. So I can multiply those, and I get 10 on, what's that, 10 on 9. U is equal to x cubed minus 1, x cubed minus 1 to the power of 3/2 plus some c. So there's my antiderivative. Yeah? So we use this process a lot. All right? Typically it's whenever we're going to have a product of functions. If we have a product of functions, we don't have a product rule for anti-differentiation. All right? So the nearest we can do is try to remove one of those functions, remove the product to make it just one function. All right? So again, 3x e to the x squared is another good example. I've got a product of functions. I can't do much with that. E to the x squared, what do I do with that? So if I put u equal to x squared, du dx is equal to 2x, which means that du is equal to x dx. So if I now come to my rule, I've got a 3 there I can bring out the front. I've got e to the x squared, which is just e to the u, because x squared is u. And then the green part, the x dx, is there, x dx, and that's just du. So now again, I've got a relatively straightforward function to anti-differentiate. The antiderivative of e to the u is just e to the u. So that's just equal to 3 e to the u plus some constant c. And u is equal to x squared. So it's never going to be acceptable to leave your final answer in terms of u, because that's something we introduced. All right. What about something like C? Very messy again. Again, you're looking to make your substitution. A part of you might want to go u is equal to x squared plus 2x to the 3. But if I differentiate that, that's not going to be present. The derivative needs to be present. So instead, we just cut it back a fraction. And what happens if u is equal to x squared plus 2x? Well, du is equal to, du dx is equal to 2x plus 2, which is the same as 2 times x plus 1. And x plus 1 is the term in my numerator. So now I could rewrite, take the x across, dx across, I get x plus 1 dx. If I bring the 2 back, I get a half du. So a half of du is equal to x plus 1 dx. So there's the numerator. So now my antiderivative, 1 half du covers that and that, which leaves me with a 1 there and u cubed on the bottom, which is this section here. So now equals antiderivative of u, well, let's bring the half out the front, u to the minus 3 du, which is equal to 1 half, add 1 to the power, u to the minus 2 on negative 2, plus some constant, minus 1/4 of u, which is x squared plus 2x to the power of minus 2. We might write 1 on 4 x squared plus 2x squared plus some constant c. Okay? Alright, next one we want to have a look at is a couple of one involving some trig functions, and they're nice typically if we have a sine and a cosine present. Well, you know the derivative of sine is cos and derivative of cos is sine, so we have that derivative present relationship. So we're going to look at the more involved expression, which is cos squared. So if u is equal to cos x, derivative of cos x.
What are you doing?
So derivative of cos x is, derivative of cos is minus sine. So then du, I'm going to put a negative du, is equal to sine x dx. So now, there's my sine x dx. So negative du, which is sine x dx, and I've got cos x, and I substitute that in, I get u squared. So I'm just clearly just going to have negative of u squared du. Antiderivative of that is add 1 to the power and divide. And u was equal to cos x, so we get the negative of cos cubed x on 3 plus some constant c. Alright. So I guess this is just a formal explanation of the process, how we substitute for the function u and it becomes a function in terms of u, and we differentiate with respect to u instead. So it's called our substitution rule. Let's do a couple more. All right. So what have we got here? Find an antiderivative for the following. So initial reaction is, well, let's put u equal to x squared plus 4x. And let's just work through that. U equal to x squared plus 4x. If I differentiate that, 2x plus 4, the problem I've got is there's no 2x plus 4 there. Okay, so it's not going to work. So instead, let's rub all that out. What we might want to do instead is, okay, maybe we can get it into a perfect square form in the denominator, because that takes me towards a tan function. So if I complete the square, so what happens? That's the same as 2 over x plus 2 all squared. So it's plus 4x plus 4, and I've got 3 left over, haven't I? So that's the equivalent expression there. Now this takes me back to that earlier example. If I put u equal to x plus 2, du dx is equal to 1. So du is just equal to dx. So now I can write this expression as, let's do it a step at a time. I'm going to put the 2 out the front, 1 over u squared plus 3. So now if I bring a 3 in there and divide by 3, I've got 3 over, or it's got to be a over a squared, isn't it? So that needs to be root 3 there. So let's undo that. Let's just go back a fraction. Let's rub that out. So what I want to do is I want to write that denominator as u squared plus, oh, that'll do in yellow, root 3 squared, which means I need a root 3 there. So I'm going to divide by a root 3 there. So now it's a over a squared plus x squared. All differentiated with respect to u. So the antiderivative of that is 2 on root 3 tan inverse of u on a. Now, we're just going to put our square root function in there. So 2 on root 3, so I might write that as 2 root 3 on 3 tan inverse. And to be honest, examiners are very comfortable with you leaving our expressions not rationalised. I guess the only challenge is sometimes matching off an answer with a CAS or a multiple choice response. If it was a multiple choice response, they'd leave it in a rational form more than likely. But that's fine, or you can put your root 3 on 3 at the front sort of thing. Okay, so you can see hopefully that combination of getting the function here into that a squared plus x squared form, and then using a u substitution to tidy that off. This one here, again, you might try and put u equal to the negative x squared minus 4x plus 9, but the derivative of that of negative 2x minus 2, we can't manufacture that in the denominator, in the numerator, so it's not a valid process. So we'd have to come up with an alternative. What's our alternative? Well, with the square root function, we should be thinking straight away, maybe it's a sine inverse. So let's complete the square on. I'm going to put the negative out the front so I don't confuse myself with negative signs. If I complete the square on that, I get x plus 2 all squared. So it's plus 4 minus 4 minus 9. That gives me a negative x plus 2 all squared minus 13 plus 13 when we put that in, yeah? So now I can write that as, I'll bring the 2 out the front, 1 over the square root. 13 I can write as root 13 squared minus x plus 2 all squared dx. So there's my function. There's my integral that I need to work out. That's a 2 there. So we can do the same sort of thing, isn't it? X plus 2, if I put u equal to x plus 2, well then du is just equally equal to dx, so that's a straight swap. So we could write this function as 2 outside of 1 over square root root 13 squared minus u squared du, which is simply equal to 2 sine inverse of x on a, which is 2 sine inverse of x plus 2 on a, which is root 13. So you could rationalise that expression, plus a c, of course, but not crucial this time, okay? The final little substitution method that we use for our u substitution is sometimes when we have linear functions, and it's that linear function in underneath a square root or raised to a power, that sort of thing. And whilst it might not seem as if it's a valid process, it makes a massive difference. So if we just have a look at these two here now, so if we just go through the process and put u equal to 3x minus 4, du is equal to, or du dx is equal to 3. So I'm going to put du equals 1/3 du is equal to dx. Okay, so there's my dx term. All right. 3x minus 4 under the square root sign, I've got that covered for there. I've got 2x plus 3 here. So in here, so I'm not going to come across here, if u is equal to 3x minus 4, well then u plus 4 is equal to 3x. So u plus 4 on 3 is equal to x. Yeah? So what's 2x plus 3 equal to? So if I multiply that by 2, therefore I get 2u plus 8 on 3 is equal to 2x. Add 3, which is 9 on 3. Therefore 2u plus 17 on 3 is equal to 2x plus 3. And now I can replace the 2x plus 3. So this integral becomes, I might take that third out the front, 2u plus 17, which is the 2x plus 3, times the square root of 3x minus 4, which is the square root of u, times dx, which is 1/3 du. Yeah, so let's just have a good look at that. 1/3 du is there, and that's the dx term. All right. Square root of u, that's the square root of 3x minus 4, and 2x plus 3 is an equivalent form of 2u plus 17. It doesn't look a hell of a lot better, but the nice thing is this u now is just u to the half, and I can multiply that through. So bring this third out the front as well. I get 1/9. 2u times u to the half is 2u to the 3 on 2 plus 17u to the half du. Yeah, so now it's a much simpler expression to integrate. So I'm going to have 1/9 out the front. I'm going to have, add 1 to the power, 5 on 2, divide by 2, which is 2/5. So I'm going to put a 4u to the 5 on 2 over 5 plus u to the 3 on 2 over 3 on 2. So I get u to the 3 on 2. I'm going to divide by 3 on 2, which is flip it upside down. 34 on 3 times 1/9. I could take things out the front here. Be interested to see what our CAS gives me. So what if we take 1/15 out the front? So I get 1 over 1/9 times a 15th is 1 over 135 outside of. I'm going to multiply that 5 by a 3, so I get 12 u. U is equal to 3x minus 4. 3x minus 4 to the 5 on 2 plus, multiply that expression there, the 3, by 5 to make it a 15th. So 34 by 5 is 170 plus 170 times u, which is 3x minus 4 to the 3 on 2. There. Now, we can factorise this, so let's have a look at step at a time. If I have 12 on 170, 2 is a common factor. Might have to go a bit smaller here. 2 on 135 outside of 3x to the minus 4, 5 on 2, 3 on 2. 3 on 2 is a common factor. So we can go 3x minus 4 to the 3 on 2 out the front of. So I've got already taken a 2 out, so I've got a 6 times 3x minus 4 to the 2 on 2, plus I've taken a 2 out the front, so that's 85 times 3x minus 4, that's a 1. So equals 2 on 135 out the front of 3x minus 4 to the 3 on 2 times 18x, I've got 18x minus 24 plus 85 is 61. How does that look? That looks pretty good, and I know it's pretty good because I had checked it on the CAS, fellas. So that's nice. I'm glad that's worked out. So look, there's a lot there, isn't there? So the algebra of this, the factorising and simplifying from this section here, just the substituting and I guess substituting in for the function to make it more accessible and integratable, if that's the word. But yeah, so look, bit there, stop it, rewind it, have a look through, work through the algebra yourself. I did take a few little shortcuts in here, just in terms of factors and things like that, so maybe slow it down a bit and work through it. All right, let's do B before we wind up. That square root function, again, the square root function is a mess, and it doesn't help us a lot. So, and technically speaking, it doesn't seem to help us. If u is equal to 3x minus 1, du dx is equal to 3, du 1/3 equals dx, and I'm going to get u plus 1 on 3 is equal to x, yeah? So that'll now allow me to substitute for all of those terms. So x squared is going to be, I'm going to have a 1/9 at the front, u plus 1 squared times the square root of u. There's a third there somewhere, 1/3 to u. So I'm going to have a 1 on 27. I'm going to expand this, u squared plus 2u plus 1 times u to the half du. Let's get an integral in there. So I get 1 on 27, so u to the 5 on 2 plus 2u to the 3 on 2 plus u to the half. And now I can anti-differentiate. Outside of u to the 7 on 2, so I'm going to have 2u to the 7 on 2 on 7 plus, it becomes u to the 5 on 2 over 5 on 2, so the 2 becomes a 2/5. 2 times 2 is 4 on 5. U to the 3 on 2 on 3 on 2, the 3 on 2 flips, so it becomes plus 2u to the 3 on 2 on 3. All right, so 7, 5 and 3, common denominator. 105 I'm going to go with, may not be, or there's a 2 on the top we can take out. I wonder if there's a smaller one than 105. Anyway, that'll do us. So we will, look, to be honest, I'd be pretty happy with those, but let's have a good go at this. I've got 1 on 27. I'm going to have 2. I'm going to put 2 on 105 out the front of, I'll just leave everything in u for now. I've taken a 2 out the front, so that becomes a 15 u to the 7 on 2 plus 21 times 2, because I took 2 out the front. 21 times 2 is 42 u to to the 5 on 2, and 35 u to the 3 on 2. So I can take, so I'm not too sure what 27 105s are. We'll see if we can get something to cancel. Outside of, u to the 3 on 2 is a common factor. So instead of putting u, I'm going to put my function. U was equal to what? U is equal to 3x minus 1. 3x minus 1 to the power of 3 on 2 out the front of 3x minus 1 to the 4 on 2, which is squared. Oh God, this is really bloody involved, isn't it? I'm not going to simplify this, boys. I don't reckon we would have to. I wonder where I got this example from. So, going to